Let's have a quick comparison with a one-shot microscopic simulation. There are a couple of ways to run a one-shot microscopic simulation, and we'll start from the basic version. In this basic type of microscopic simulation model, we have a predefined set of shortest paths set aside before we begin running the model. The user can specify which one they would like to use. The proportion, or split percentage, or assignment percentage is defined as well. As the simulation is running, vehicles are being generated, and at that generation, the vehicles are assigned a path. Those paths are selected from the predefined set of paths following the defined percentage. The simulation follows this process until it ends. There are no iterations, and once the process plays out, the simulation is over and the statistics are collected and reported. This is very different from a DTA model's structure. Without iterations, you are unable to take the information from a single simulation and use it to adjust the path for the users who may have altered their behavior in order to improve their travel time. Additionally, in the middle of the simulation, congestion is highly likely to build up as there is a lot more traffic entering the network than in the previous time frame. In the microscopic simulation, vehicles continue to select the same paths following the same split percentage so that congestion is artificially inflated. An improved version of this basic model is still a one-shot simulation with no iterations, but periodically within the simulation, a snapshot of the network conditions is taken and is used to update the shortest path. Therefore, as the simulation progresses, if traffic conditions become more congested, the update will path vehicles through less congested routes. As more vehicles are generated, they are also given these updated shortest paths. In this case, the shortest paths are more sensitive to the congestion patterns. From a behavior standpoint, the drivers are receiving real-time information at departure and selecting a best route when they are leaving. If all the vehicles are given information this way, that means that all of the drivers have access to real-time information. However, none of them have any sort of memory or learning behavior, and once they are given the shortest path, they embark on it and follow it to the end. In this kind of one-shot simulation without iterations, there is this kind of specific behavior assumption within. This is not necessarily the most representative of what the majority of travelers would do. Although nowadays the market share of real-time devices is quite high and increasing, the majority of drivers still rely on some sort of habit or experience formed through using the system over time. The third variation of the one-shot simulation is similar, with the difference being that newly found shortest paths can be applied to vehicles already in the network. Basically, when new vehicles are generated, they are given the shortest paths available to them. Additionally, these paths can be given to vehicles that were generated previously and may be stuck in traffic, allowing them to divert from their original route. This is another level of improvement over the previous versions, with the goal of limiting the number of vehicles stuck in traffic. From a behavior standpoint, this can be interpreted as some kind of real-time information given to the drivers en route. However, without iterations, this is still a one-shot simulation that assumes there is no learning or adaptation of behavior taking place, and that drivers only react to real-time information.